Welcome to Biology 159 and the first video in our video series. Today, I'll introduce you to the basics of scientific investigation and experimental design. Today's objectives, we'll discuss the differences between a null hypothesis, prediction, and scientific theory. We'll describe why replicates are needed in a biological investigation, summarize the differences between process and sample variation, and distinguish between mean and standard error for a data set. I'll then explain how two means are determined to be statistically different. The scientific method begins with observations. For example, we know that swans are white. So our observation would be all swans appear to be white. Next, you want to gather background information. Everywhere we look in the United States, we see white swans. You then want to identify a question. Is it true that all swans are white? Or is it possible there may be a swan that is another color somewhere in the world? You then want to form a hypothesis. A hypothesis is a proposed explanation for a phenomenon being studied. A scientific hypothesis needs to be testable and falsifiable. Falsifiability means that the hypothesis has a possibility of being wrong. This prevents us from drawing conclusions in the absence of evidence. So our hypothesis would be, we hypothesize that there are swans of other colors. This hypothesis is falsifiable as it may be true that swans are always white in color, and we may not find any swan that is of any other color. The null hypothesis states that there is no statistical difference between specified populations or observations. So what this means is that no matter where we look in our example, we will always find white swans. Therefore, our null hypothesis is all swans are white. Once you have your hypothesis and you have your null hypothesis, you can then make predictions. Predictions are statements about patterns, trends, or differences between groups. These are measurable differences. Ideally, for any hypothesis-driven question, you will generate multiple hypotheses, which you can then attempt to falsify by generating predictions, collecting data, and performing statistical analysis to determine if your prediction is true. So for our prediction, we will predict that we will find a blue swan. Once you make your prediction, you test the hypothesis through experimentation or observations. You then interpret the data and you communicate the results. No matter what, you always communicate your results. So we go out into the world and we start making observations. And lo and behold, in Australia, we discover a black swan. So it turns out that our hypothesis that there are swans of other colors is true. And our null hypothesis that all swans are white turns out to be wrong. It's false. However, our prediction that we would find blue swans also turned out to be false because we found that there are black swans. Now, this doesn't mean that our prediction is absolutely false. It may turn out that we would find a blue swan someday. It just happens in this case that we found a black swan. So in science and in everyday use, we have this word called theory. The common day use of the word theory usually means an idea or a hunch about a topic. For example, let's say that you and your friend want to go to the Alabama and Tennessee game that takes place every October. And you tell your friend, my theory is that Tennessee will win. This is not what we're talking about when we say theory. A scientific theory is a coherent explanation of a phenomenon in the natural world that has been repeatedly verified through experimentation. Theories are used to explain what we call scientific laws. Now that we have an understanding of null hypothesis, theories, and predictions, it's good to understand that when we do scientific experimentation, there are two sources of variability we need to consider. You have process variation, natural variation among organisms, and this can be intra or interspecific. Now, interspecific variation is differences between individuals of the same group. So some people have blue eyes, and some people have brown eyes, and some people have green eyes. And that variation is considered intraspecific within the species or within the group. Another one is interspecific variation, and this is differences between individuals of different groups. If we were to compare a group of human characteristics to that of a group of chimpanzee characteristics, this would be interspecific variation. To account for this type of variation, you want to make sure you take as many replicates as possible. So you also have sample variation, which is measurement error. To capture the amount of variation in data, scientists calculate things such as the measure of central tendency. These are mean, median, and mode. For our purposes, we're going to be calculating the mean, or what is also known as the average, by adding all our replicates you sample and dividing by the sum number of replicates. So if you take 10 measurements, you're going to add up all 10 of those measurements and divide by 10. We also have measures of dispersion. This is the standard deviation and standard error. Standard deviation is a statistical measurement of the dispersion of your data around the mean, while the standard error takes the sample size and standard deviation into account and can therefore be used to quantify uncertainty in a mean, and is defined as an estimate of how closely the sample mean represents the true population mean. So what does all this mean for us? Let's say we were able to acquire the height of every man within the United States. We would then know what the true average height of men within the US is. However, that's not possible. So we have to make do. And we decide that we're only going to sample 100 men. And we plot that. Well, what would that plot look like? The plot would look very similar to what we see in the top left up here. Now let's say we increase our sample size to 200 men. It's going to look more like the plot in the top right. Now we increase our sample size even further to 1,000 men, which now looks like what we see in the bottom left. And you could keep increasing this exponentially until you end up with something that looks very similar to what we see in the bottom right, which is a normal distribution bell curve. Now let's say you want to compare the differences in the average height of men from Chicago and New York. How could you tell if these differences in height are statistically significant from each other? The best way is to perform a t-test. And to explain the t-test to you, I found a video from the YouTube channel Bozeman Science, and he goes into great detail explaining the history of a t-test and how it works. He also demonstrates how to conduct a t-test in Excel, which you will use for your homework assignment. So without further ado, here's the Bozeman video.
The t-test was developed by William Seeley Gossett. He worked at the Guinness Brewery over 100 years ago, and he developed this test to determine things like the difference between barley yield. Now, he wanted to publish this statistical test to share it with other statisticians, but the brewery was nervous. They didn't want him to publish. They didn't want him to give away any secrets. He finally convinced them, but he had to publish under the pseudonym Student. So instead of this being known as the Gossett's t-test, it's known as the... So in this video, I'm going to start by conceptually showing you what the t-test is. I'll then show you how to calculate the t-value, run a t-test, and then finally, how to do a t-test in just a few seconds using a spreadsheet. So imagine I have two fields of barley, field 1 and field 2, and I want to compare them, but I don't want to cut down the whole field. I just want to do some samples. Samples from 1, samples from 2. So I could get a sample from field 1. Now it won't be a perfect normal distribution like this. It's going to be more of a histogram that looks like that. And then I'm going to get a sample from field 2. Now, which one of these has a higher yield? Well, we could figure out the mean, we could figure out the average of each of those samples, and it looks like the average in field 2 is higher than the average in field 1. But that's only part of the picture. The mean only tells us so much, because we could have different distributions, and depending on that distribution or the variance within that sample, there could be a statistically significant difference between the two or not. And that's where the t-value comes in handy. It's really a ratio of signal to noise. Signal is going to be numbers that tell me the difference between these two samples, and noise is going to be numbers that kind of get in the way. So how do I figure out the signal? Well, the easiest way to do that is simply find the difference between the two means. And so if I calculate the mean in sample 1, we'll call that x bar 1, and x bar 2, the absolute value or the difference between the two, is going to tell you how much signal there is, how much difference there is. Now, how do we get at the noise? That's going to be in the variability of the groups themselves. And so the factor is going to look something like this. What is S1? That's the standard deviation. Remember, that's how far our data is spread from the mean. But we're not only taking the standard deviation, we're actually squaring that. That gives us something called the variance. And so if I increase the variance, that's going to lower my value. It's like giving me more noise. Now, the other factor in here is going to be the number of samples that I'm taking. As I increase the number of samples, that will actually increase the signal up to a point. And so again, the difference between the means is going to give us more signal, higher t-value, and increasing that variability is actually going to decrease it. So let me show you how to calculate that t-value. I'm using Excel, but you could use Google Sheets or even your TI calculator. So if you look at these two samples from field 1 and field 2, can you tell which one has a higher yield? It's really hard just looking at it. Is there a difference between the two, and how much is that difference? So we'll use the t-value to calculate that. First thing we have to figure out is the mean. So in a spreadsheet, you hit equals average instead of mean. I'm going to put left parentheses, and now I'm going to select that entire sample set from field 1. End parentheses, and then I'm going to get a mean of 15.38. Now I can select that and drag over, and now I get a mean of 15.68 in field 2. Next thing I have to figure out is my standard deviation, so that's equals STDEV, left parentheses. I'm now going to sample that field 1, and now I put end parentheses, so we're going to have a standard deviation of 0.3124. I'm now going to apply that into field 2's data set, so we have a higher standard deviation. Remember, I now have to calculate the variance. To do that, you have to square the standard deviation. So I'm going to select that cell and bring it to the second power. So there's my variance for field 1, and now here's my variance for field 2. And then finally, I have to know how much data I'm actually collecting. So if you hit equals count, that'll count the number of data. And so I'm going to count those, and we get 16. So we got 16, and then it's going to be 16 in the next one as well. Now you could use a spreadsheet to calculate this. You could do it by hand. It takes a long time to figure out standard deviation by hand, so I'd encourage you to use something like a spreadsheet. Now I have all these values. I'm simply going to plug it into my t-value like that. So we've got the signal on the top, so I'm going to find the difference between these two, and then I'm going to figure out my noise on the bottom. Remember, you have to divide this, add it, and then take the square root of that. So if I do the work for you, we've got a signal of 0.30, a noise of 0.13, so I've got a t-value of 2.3. What does that mean? Since it's higher than 1, that means there's more signal, there is noise. So I'm going to put that over here to the side, because this video is not about the student's t-value, it's about the student's t-test. So now we're going to run a t-test. What are we testing? We're testing our null hypothesis. Just like we do in a chi-squared test, what we're going to start with is a null hypothesis that says there's no statistically significant difference between the samples. In other words, any difference that we would find is simply due to chance. You then identify a critical value, a number. If our t-value is lower than that, then we don't reject our null hypothesis. But if we get a t-value that's higher than the critical value, then we reject our null hypothesis. There must be an alternate hypothesis. There could be something going on between these two fields. Now, how do we find that critical value? We'll use a t-table that looks like this. It looks confusing, but it's really not that bad. So this would be for a two-tail test, and I'll show you what that means in just a second. The first thing you have to know is what probability are we going to use. Generally in science, we'll use the 0.05 probability. So that's going to be this column right here. What does that mean? Well, this is an inferential statistic. It means if we were to do this sample 100 times, 95 of the times we would reject the null hypothesis, and only 5% we wouldn't. And so it has a lot to do with chance. So I'm going to use that 0.05. Now we have to figure out what row we're going to do. And to do that, we have to know how many samples we collected and figure out the degrees of freedom. So the degrees of freedom is going to be the samples of N1 and N2 minus 2. So since we took 16 from each, it's going to be 32 minus 2, or 30 degrees of freedom. So here's our critical value. Our critical value is going to be 2.04. So is our t-value higher than that? So this is where we're doing the actual t-test. Are we higher than 2.04? We are. And so what does that mean? We're going to reject our null hypothesis. That means there is something statistically significant between these two sample sets. Now it's not much higher than that. Remember, it's just 2.3. And if we were to look over here to the 0.025 probability, we can see that we're actually lower than that. So we're not positive, but we're pretty sure that there's something statistically significant between these two. Now that was a lot of work. We had to calculate our variance, our means, our sample size, and then find this table. The nice thing about a spreadsheet is it can calculate a t-test very quickly. So what I'm going to do is put t-test here, and then I'll just write in this next cell equals t-test. So there are 4 things I have to put in for a t-test. The first one is going to be my sample set, we'll say from field 1, so I'm going to select that. Then I put a comma in. Now I'm going to grab my data set from field 2. And then I'm going to put another comma. We're doing a two-tailed test, and this is an independent test. I'll show you what that is in just a second. But you can see in just a few seconds, we've calculated my probability, or my p-value. What is it? It is 0.026. What does that mean? It's slightly above 0.025 and somewhere in between 0.05 and 0.025. What does that mean? In just a few seconds, we're able to realize that we need to reject that null hypothesis. So it's really simple in a spreadsheet to do a t-test very quickly. Now we did an independent t-test, or an unpaired sample. What does that mean? We had 2 different fields that we were comparing. So you could be comparing, for example, 2 different populations. You can also run a paired t-test, and you would have to select that when you're running the t-test. What would that be? It's if we're sampling the same population twice. So maybe we're looking at field 2, but then we're applying a chemical and looking at it again. That would be a paired test. We're also doing a two-tailed test. And so when we're figuring out that probability of 0.05, you can think of it like this. This is the 0.95 that we would reject the null hypothesis. And that 0.05 is actually split between the 2 tails, because we're not sure which direction that variance is going to be. You could also run a one-tailed test if you're sure of the directionality, but you have to be cautious when you're running that. There are a few assumptions you have to have when you're running a t-test. Number 1, we should have a normal distribution in both the population and in the sample, but it works really well with a small sample size. We also should have similar variance in each of those samples. And then when we're looking at the data points, we should have roughly the same number of data points on either sample. And then finally, this works good with low numbers, but you generally want to be in the 20 to 30 range when we're looking for samples. If we go much higher than that, instead of using a t-test, we'd actually use a z-test.
Bozeman showed us how to calculate the variance, but for our purposes, we're not worried about the variance. What we are worried about is the standard. The standard error is the standard deviation divided by the number of samples in each field. So to calculate the standard error, what you would do is you would type in equals and select your standard deviation, divide by the square root, and select your number. Close your brackets and hit enter. Just as we did with all our other calculations, you're going to grab the corner and you're going to drag it over, and that will also calculate the standard error for your field 2. Something else Bozeman didn't cover is how do we visualize this data? Well, the best way to do it is to build a bar graph. And how we're going to select for our bar graph, first we need to select our field locations. So click on field 1, then hold down the command key. I believe this is going to be your control key if you have a regular PC. Once you click field 1, hold down command and then click field 2, and then you also want to click the mean for field 1 and the mean for field 2. Then you're going to let off the command key, click on charts, go over to your column chart and select a column chart. Now, we have a plain chart here. We don't need this series number. This isn't important for us. So you can go ahead and delete that. Now what we do want is we want to name our axes. We also want a chart title. So go up to chart layout, go to chart title, select title above chart, and then for your axes, go to your horizontal, title below axis, then go back, go to vertical, rotated title. For our chart name, we're going to name it Comparison of Field Sites. And then our x-axis title, we're going to name it Field Site. For our horizontal, we'll name it Barley Yield. And one thing that's missing in this chart is our error bars, and we need our error bars to determine whether or not there's a statistical difference between the two field locations. Now to add these error bars, we click on the chart, we go to chart layout, and select error bars with standard error. Now when we select this, it gives us an automatic error bar that does not include our actual standard error. And we need to select that actual standard error. And the way we do this is we go to error bar options, you go to custom. Now in your PC, if you have a standard PC and not a Mac, this window will open up in this location here. But it's going to be the same steps. So you select custom, specify value, and you're going to get a box that opens up here. You're going to delete whatever's in that box. You're going to hold Control, or in the case of a Mac, you're going to hold down Command and click the standard error value for field 1 and the standard error value for field 2. Then go down to your negative error value, and you're going to do the same. You're going to hold down Command or Control, depending on if you have a PC or Mac. Select again the standard error for field 1 and the standard error for field 2. Now what this does, you hit OK, and now your standard error bars are set correctly. Now now after you've done this and you've set your specific range, go ahead and click OK. Now what this has done is when you were selecting the positive values, it was controlling this aspect of the error bars. When you selected for the negative values, it was selecting for this aspect of the error bars. Now that you have an understanding of the scientific method, and you know how to use Excel to find out if there's a statistical difference between two means, we have a homework assignment for you. A Doodle poll link should have been emailed to you and/or is located on Canvas. Find and open this link. Pick which homework version you want. Click and sign on that version. Then return to Canvas. Find the homework folder, and in that folder locate and download your selected homework version. When you open your homework version, you should see something similar to the below data in an Excel document. Over a 10-day period, you recorded toad calls per hour at 2 different time points. In this example, 6 a.m. and noon. You want to know if there's a statistical difference in the number of toad calls between the 2 time points. You need to calculate the mean, standard deviation, and standard error for each of the replicates below. Then perform a t-test. Finally, create a column chart showing the mean and standard error bars on a labeled figure. Based on your calculations and t-test results, is there a difference in the number of toad calls between the 2 time points in this pond? Explain your results. You should print this out and turn in all data, calculations, and your graph to your TA at the beginning of the next lab period.